What's up, geeks, and welcome to the channel. It goes without saying that graphs are one hot topic that you will most likely be asked about during coding interviews. In one of our very first graph introductory videos, we explained what components are and what a connected component is. And as a reminder, a connected component is a connected subgraph in which every vertex can be reached from any other vertex from within this subgraph. So, suppose we are given a graph represented by an n times n matrix. This matrix will store ones and zeros. A 1 means that these two vertices are directly connected, and a 0 means they aren't. We are asked to find the number of connected components inside this graph. How do we do that? Note that the matrix we have here can be represented by the graph next to it. You see, it doesn't matter if instead of ones and zeros we had actual edge weights. We don't need that information anyway. All we care about is knowing if a vertex is connected to any other vertex, no matter the weight connecting them. Okay, so one obvious solution for this problem is traversing the graph using any traversal technique you want. We already covered several of these in previous videos, feel free to check them out. So, we will go ahead and start by traversing the graph starting from any vertex. Every time we traverse a vertex, we will mark it as visited. When there are no more vertices to traverse, we increase the number of connected components we have by 1, because all the vertices we just traversed belong to one component. If we pick any other vertex from that component and start our traversal from there, we will visit the same vertices, since that's what a connected component is by definition. Now, we know what are the vertices that make our initial graph, and if a vertex was not visited during that initial traversal, it means that it belongs to another component, right? So if we rerun the traversal logic starting from that unvisited vertex, then we will be traversing a new component. This logic is then repeated for all unvisited vertices of the given graph until we obtain the number of connected components of that graph. To implement this solution, and as I mentioned, we will have to go through all the vertices we have and traverse the ones that have not yet been visited. To keep track of whether a vertex was visited or not, we went ahead and created a 1D array of Boolean type. Now, every time we enter this if statement, it means that a connected component was found and that we should increase our connected components count, which is the value we are returning by 1. Why? Because if we enter the first time, set that count to 1 and all our vertices were connected, then we will never enter this if statement again, since all our vertices will be marked as visited. We will only enter this code block more than once if and only if multiple components exist in the given graph. The last missing piece is the actual traversal logic, which can be anything you like. In this example, we went with DFS since it's the more compact solution, meaning we are using recursion, and for every vertex we check, if it is not visited, we mark it as visited and proceed to traverse its neighbors. You see, the problem we just managed to solve is at the center and basis of every connected component problem out there, no matter what shape this problem takes. Understanding the logic we just wrote is fundamental in tackling every other problem related to this topic. And to give you an idea on what I mean by this, suppose the interviewer provides you with a 2D n times m matrix also filled with ones and zeros and asks you to count the number of islands in that matrix. To visualize this, suppose that is the matrix we were given, meaning the areas in red are considered islands on that matrix, making the total number of islands equal to 4. Keep in mind that an island is formed by connecting adjacent cells containing ones horizontally or vertically. You see, this is not an adjacency matrix because n is not equal to m, and the indices of rows and columns cannot be considered as vertices. However, the main idea behind this new exercise is the same as the previous one. We are given a large structure and we want to traverse each element inside it. Some of these elements will be linked, hence belong to the same component, some will not. Every time we switch to traversing a new component, we increase the count we are looking for. That is the main idea behind it and the main logic you need to focus on. So, to solve this problem, and as I mentioned, we want to traverse all the elements of the given structure. In the previous example, it was a set of vertices, so we traversed that. In this example, each element or cell we have is independent of the other, hence we need to traverse all the cells present inside the provided 2D matrix. Then, every time we encounter a non-visited element, we proceed by traversing that element and its adjacent element. To keep track of visited and non-visited cells, we are using the information stored inside the cell itself, which is the ones and zeros. Since an island is a bunch of ones, after visiting a cell we turn the 1 into a 0, marking this cell as visited. After every traversal, if more non-visited elements are still encountered, it means that we discovered a new island and that we need to increase the resulting count we are returning by 1. Now, to traverse a single island, we went with DFS as well, and to mark its elements as visited, we are simply switching the 1 to 0 as we just mentioned. To traverse the adjacent elements of the cell we are currently at, we are simply calling this same method recursively by incrementing or decrementing the appropriate index, since, as mentioned in the question, an island can be propagated vertically or horizontally only. Finally, before we make any of these calls, we need to make sure that we are still within the boundaries of our matrix. Because you see, in the calls we just added, we are incrementing and decrementing the current position blindly, and without the is not valid check we just added, these calls will lead to out-of-bounds exceptions. Now, before ending the video, I want you to take note that this solution can't be used to solve the first problem and vice versa. Why? We already mentioned that the first solution can't be used here because n is different than m, but why can't this one be used there? Well, take this n times n matrix as an example, given that m equals n here, and by making use of the same definition we had in the first problem, we can derive the graph you see to the left from this matrix. We can clearly see that this graph is connected and hence represents a single component. However, if we make use of the logic we implemented in the second problem, it will return 5 islands. So the idea and methodology behind these problems is the same, but the implementation will differ. The link to the LeetCode problems we solved today can be found in the description below. Let me know your thoughts and suggestions for upcoming videos in the comments section. And before we sign off, we would like to mention that we launched our Patreon this year. For more info, you can click on the link in the description below. And that's it for today. I hope it was helpful. Thank you guys for watching. Take care, and I will see you in the next one.